this is the title of my talk today, but then after I come here yesterday or the day before, I realized this is a very general topics, and I realize there are many experts in the audience. So before I start, I want to ask, who has ever heard of light sheet microscope? Yes. And who has ever heard of oblique plane microscope, OPM? Structural illumination microscopy? Wow. And a combination of OPM and SIM, or light sheet and SIM. Good. So actually, I want to switch my topic to this one here, because I feel, general talk of light sheet might be very boring for you guys here. So I'm going to talk about some recent development in the lab, which is pushing the limit with structural illumination in light sheet fluorescence microscopy. So basically, we are going to combine the OPN and SIM here. And this is the work mainly done with my colleague Jui CHANG and also Recto Fiocca. Of course, this is my outline, and I would keep the introduction of the light sheet fluorescence microscopy very short. And I'm going to go through the OPM, the structural illumination microscopy, and the combination of SIM and light sheet fluorescence microscopy. And if time permitted, I would like to talk about this live projection imaging, which we actually published some years ago. And we feel actually it's a little bit underappreciated. So I hope that I have some time to talk about that. I forgot to start my alarm, so I hope I don't talk too long. Okay, so I can skip all these slides, it's for more general talk, but I still want to start with these slides here. I think most of you know about this slide, that there is a trade-off in fluorescence microscopy. Of course, we only have limited of photons, and we always need to compromise between all these parameters, like the spatial resolution, the temporal resolution, the photo-toxicity, or the image depth. So imagine you want to do super resolution. For example, you want to do a single molecule localization microscopy, then you actually need to image something long. So you kind of like sacrifice the temporal resolution. And sometimes if you want to do something deeper, then you probably need to increase your laser power, so increase the phototoxicity. So which means that you need to use these photons more wisely, and then you need to tailor your experiment and a microscope to get the information you want to get. So in a conventional AP fluorescence AP configuration, no matter it's a wide field microscope or it's a confocal microscope, you only have one objective lens. So the illumination and detection are actually along the same direction. So now, imagine these photons or the fluorophores are your bank savings. And every time you want to image just one single plane, which means like it's like you want to take €1 from your bank account. But since the photons here and here are wasted, you don't see them, you don't take the money out, but actually you pay this money to the bank. You pay a lot of commission. And then if you want to take a 3D stack, now you want to go through each plane here. Every time you take €1, you actually pay more to the bank. So I think no one wants to do that unless you are working in the bank. And I guess no one here working in the bank here. So in the light sheet microscope, we use these photons more wisely. So we basically separate the illumination from the detection, and we shape the illumination to a sheet of light, and it only overlap with the image plane. So now this is again your bank account, your bank savings. You want to take €1 out, you don't need to pay this commission to the bank. And this photo-bleaching is actually dramatically decreased if you want to acquire stack, because you want to move this sample up and down, or you want to move the light sheet up and down. So to do a light sheet microscope is actually pretty simple. Basically, you separate the illumination from the detection, and you use a cylindrical lens here and all the detection path to shape the beam into a simple light sheet. And the detection path is it's basically very simple and the same as a fluorescence microscope. You just have a filter wheel, a tube lens, and a camera. And of course, the sample is held from the top. You sometimes put a sample in agarose, and then you put a sample down here. I don't know how many biologists are here. I don't know if you know what is a cylindrical lens, but the cylindrical lens basically is a convex lens or concave lens that is only have a curvature in one dimension. So before I come here, I borrow one conical tube from the cell culture room, and then like this 15 ml conical tube, and you just fill that with water. This is actually a cylindrical lens. So for example, if I put my laser beam here, so basically, you can do light sheet from your home, from your home. You know, well, Ang's. I have been a postdoc in Ang's lab, and he always said that you can build a light sheet with a laser pointer and a cell phone. And I think now with this conical tube, it's really possible. Okay, so I talk about the photo bleaching, and here is a comparison. So this is a dice beam. It's also kind of a light sheet microscope. You can see there are separated illumination and detection objectives. And if you look at these images here, on the top is the images taken by the dice beam, the light sheet microscope, and at the bottom is the spinning disk confocal. Now it disappeared. Oh. Okay, so I want to let it play. Okay, so I want you to notice that the volume are the same here. So this is the ACE volume, which means that you now take ACE stacks, and you can see the fluorescence are almost bleach out in a spinning disk confocal microscope. So this is one advantage of light sheet microscope, that you have really low photo bleaching and low phototoxicity. The other thing is, if you notice the time here, so to acquire A volumes here with the spinning disk confocal, which is already very fast, it takes about 1 minute and 24 seconds. But with the light sheet, it only takes about 28 seconds. So this is another advantage of light sheet microscope, that you can take image really, really fast. And of course, we all know that the light sheet microscope has a true optical sectioning ability, because the overall point spread function, or the system point spread function, is the multiplication of the illumination point spread function and detection point spread function. So basically, it's this area here. And if you look at this 1 micrometer beads in agarose, this is in the Z direction, you can immediately appreciate that you now can resolve all the beads in the Z direction because of the optical sectioning ability. And the other thing is, of course, you cannot create an infinity long and super small light sheet. You always need to compromise between the light sheet thickness and the length here. So to create a thinner light sheet, this light sheet would diverge dramatically. So you always need to tune these two parameters to fit your experiment or your sample, because this light sheet length basically needs to cover your field of view. So here are some example that some images we acquired in the lab. So this is a zebrafish, and we just went through the stack, and you can see the heartbeats here. We can do this very fast. We can even do faster. This is 50 milliseconds exposure time. Of course, this is the maximum intensity projection in the XY, ZY, and XZ direction. And if you look at just one single plane, you can see how fast we can do the image here. So this is 50 milliseconds. You can see the hearts from this size getting small, 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 and it become big here. And this is about 10 frames, which is like 1500 milliseconds. And if you look at the heartbeats of a zebrafish, it's probably 2 hertz. So this actually fits pretty well with the phenomena of the heartbeats. And of course, we can also acquire The whole zebrafish, this is actually acquired with, I think, 6 volumes, and then we stitch them together. Of course, this is not new to you. And here, I just demonstrate that we can also do this live imaging here. This is, again, in the zebrafish, and our original plan was to look at the muscle fusion here, but then just by coincidence, we see this is kind of the macrophage that's crawling around in the zebrafish, and then we image this like a few hours, and you can see how the macrophage crawling around and also become blobby here, which is just very fun to look at. And then of course the other possibility of light sheet microscope is the multi-view, because now you can put a sample from the top. You can rotate this agarose gel, and you can image that from different directions. And of course, you can fuse the data together. Now you can even get the isotropic resolution here, because the Z resolution is always actually worse than the X and Y. If you can do multi-view fusion, then you can get really isotropic resolution in X and Y and Z. And you can also increase the penetration depth because of the scattering and aberration of your sample. The light cannot penetrate through, if your sample is big, then you cannot penetrate through the whole sample, and same is the detection. So sometimes you can only get a clear image of a quarter of your sample. So for example, this is a multi-view imaging of Tibolian. This is acquired by my colleague when I was in Ernst Stelzer's lab. So you can collect this data from 4 different angles, and you can collect the data up to 2 or 3 days. And of course, you can fuse them. You can do the maximum projection. You can do the volume rendering, and you can do the lineage or the tracking of each nuclei, and so on and on. Okay, and then of course you can also have 2 views, so you don't need to rotate the sample 4 times. You probably just need to rotate it 2 times. And then here is something we have done in the lab before. So for example, here, this is the XY view. You see you only get this quarter clear, and if you have the illumination from the other side, then you get this quarter clear. And if you have both illumination, then you have this half of the sample is clear. And to get this half clear, you still need to rotate the sample, but at least you don't need to rotate the sample 4 times. And of course, some people have done like 2 illumination, 2 detection. So now you don't really need to rotate the sample at all. So this is kind of a setup that you can acquire the data from 2 angles and illuminate the sample from 2 angles. Okay, so now I would start talking about OPM, just some general introduction of light sheet there. So as I said, for the conventional light sheet, you can put a sample from the top, which gives you some advantage, like you can rotate the sample, you can do multi-view fusion. But sometimes you want to work with normal cell culture dish, for example, this Petri dish here. So the original challenge is you cannot really put such a Petri dish in this chamber. And with some high resolution light sheet, for example, lattice light sheet microscope, you also cannot put these things here. For biologists, this is very easy to use. You can culture your cells here. You can put that in this small incubator. You have good temperature and a CO2 control. You have less contamination issues. So how to do that? So actually back in 2008, Christopher Dunsby has invented this OPM system. This is basically an oblique plane microscope. So the idea is in the conventional light sheet, you have the separation of illumination and detection. What if we use the same objective lens here and we create a light sheet that comes in an oblique angle and then detect the fluorescence from 90 degrees here. And of course, you immediately see that now on the image plane, your image looks a little bit tilted here. So this is a setup that he invented. So of course you have the sample here. You have the illumination comes in an oblique angle. You detect the fluorescence also 90 degrees to this oblique angle, and then you have on the image plane here, the image here looks tilted here. And you might wonder, why couldn't I just put a camera here and tilt it by 45 degrees or 30 degrees? The reason you cannot do that is because of the aberration. So you will not really get a clear image here. And fortunately, there's a so-called perfect image system or a remote focusing system. So basically, you can image this image here back here with a secondary objective here. And then now you put a third objective lens or third image system here. Now you can image this this object or this virtual image here. And there's a lot of mathematics behind that, but just want to simply say that to get a perfect condition, this perfect image system, you just need to make sure that the magnification of this whole system equals to the ratio of the refractive index, because normally we work with the sample in media or in water, but on the other side, this is probably in air. So you just need to make sure that the magnification from the left-hand side to the right-hand side match to this ratio of the refractive index. And of course, for some details, there's some sign condition and this Herschel condition, which describe that your image needs to be perfect in axial direction or in lateral direction. But in the end, the conclusion is if you make this lateral and axial magnification the same as m, and this m equals to the ratio of the refractive index, then you have the perfect imaging system. So this is kind of the perfect image system. You have the first objective, and then you image your sample here, and then you make the second magnification system. You have the second objective, you have the second tube length, and as long as you make sure that the magnification between these two equals to n1 over n2, then you have the perfect system. So when Dunsby invented OPM, we were thinking like, okay, this is your illumination, this is your light sheet, and you only detect the image, the fluorescence 90 degrees to this illumination. And of course, you have a remote focus system, so you detect the light in this direction. And then you would immediately feel that you only detect these small angles here, which means that you actually lose the NA, and then you actually lose the resolution here. But actually, this is not quite true. So actually, along this line, the fluorescence, the angle of the collection is actually this big. So you basically can collect all these angles here, but the problem is you cannot collect all these angles. I don't have a drawing here, but you cannot collect all these lights with the third objective lens. Of course, if you can have a super big NA third objective, then you can collect these angles. But practically, you don't have that. If you have a virtual mirror here that can tilt this cone here, then you can collect all the angles here. Then you don't lose the NA here. You can keep the resolution. But in the end, what people invented is if you put for example, water medium here that can squeeze this cone here, and then now you can collect all these angles here. So you don't lose the NA, so basically you don't lose the resolution from here. And now a better invention is now we have this so-called snouty objective. You can see on the top of the objective there's a piece of glass. So the glass has higher refractive index than water and air. So basically now you can collect all the lights through these third objectives here. This is actually invented by Andrew York and Alfred at Calico Labs, and this is the size of a snouty objective or the tertiary objective compared to a mark here. So now we can have such a system. So you have a illumination module, and then you have the tube lens, you have the scan lens here, you have a scanning goggles. Actually, there should be a dichroic mirror, a cylindrical lens somewhere. But essentially, you can create a light sheet here, and it goes along this path and create a light sheet here. And by using this scanning goggle, you can scan the light sheet across the sample, and then you collect the fluorescence through the same path back here. And as I said, now you have this tertiary objective or this Mr. Snouty, then you can collect all the light into this detection path. There's a very nice videos. You can Google it to see how it really works. So now you have this illumination, and the illumination goes through this a few optics, and then this is a scanner, and then you can scan the light sheet, and which will scan the light sheet across your sample, and here is your sample here, and then the fluorescence is collected through the same path back. And then because of the, so you have the first image plane here, and then through the same scanner, and then well, this video plays slower than I thought. Okay. And then you collect your image here, and since this is a perfect system, now you can image that with this third objective here, and then you can collect the image on this camera. I forgot to say that if you have any questions, I think you can just interrupt me. I know maybe this is not regular, but if I can see you waving your hands, and then if you can speak loud, maybe I can just answer the questions right away. Okay, so what we can do with this OPN system is, for example, we image the interaction of the natural killer cells and the leukemia cells here. So this is the natural killer cells in red and the leukemia in cyan. And I hope that you can appreciate that we still have very high resolution here. You can see all these synapses in very details. And we can also image this very long and also image this very, very fast. And because of the OPN, now we can put regular samples on the system. So here is a microfluidic device. So these cells try to squeeze them through this little pillar here. And we can also image that with this OPM system. And of course, we can also image something big. This is a Drosophila embryo, and then we just image that this ventral furrow formation. And you can see we image up to 30 minutes, and we also image this pretty fast. I think every, I don't remember, 15 seconds maybe. Yeah. And that's actually a whole stack. We can also do more trick here. So I mentioned that we use a scanner, a galvan mirror, to scan the light sheet to acquire the volumetric image. But actually, we can put a second pair of the goggles here. So usually, you acquire data like this. So you have the light sheet scanning across your sample here. And now with the second goggle pair, so originally you can get a field of view about 500 micrometers by 300 micrometers. And now you, with the second goggle pair, you can actually now image something 500 by 500 micros, with the field of view of 500 by 500 micrometers. So this is kind of the result we got. So this is a 100 micrometer scale bar. So this whole field of view is really 500 by 500. And then if you can zoom into all these little red box here, I hope that you can still appreciate that we still have really quite high resolution here. this OPM system is not as, this is the second OPM system we built in the lab, and it doesn't have as high resolution as the first one, but you can see we still can distinguish this whole filaments here, which means it still has relative high resolution. We can also have something here, and then we can image this pretty fast. I forgot to mention this is all 3D volumes, and what I'm showing here is just the maximum intensity projection of the volume. Okay, so now I want to talk a little bit about the super resolution, or actually the structural illumination microscopy. As we all know that there are three, basically in my opinion, there are three super resolution techniques. One is single molecule localization microscopy, one is STED, but today I'm going to mainly focus on the structural illumination microscopy. So very simply speaking is basically you illuminate your sample not at once with the, you don't illuminate the whole field of view at once. You illuminate that with the pattern. And of course you need to shift the pattern to give the signal like on and off. And then after some reconstruction, you can basically reconstruct a high resolution image here. So this is all done in the Fourier space, basically. So basically, if you illuminate your sample with these stripe patterns, and of course you need to shift that 3 times if you are doing the 2D sim, then you can increase the information in the Fourier space along this direction. And after you do the inverse Fourier transform, you can see that you increase the resolution in this direction, along the pattern direction. And of course, you can do 4 orientation or 3 rotations, and after you fuse all the information in the Fourier space, you do a inverse Fourier transform, then you can increase the resolution in all directions. So normally, to create a scene in a microscope, you probably would interfere 2 beams here, and you create these patterns. And then of course you rotate this pattern here to create to generate an isotropic resolution improvement. But the questioning is, how do you do that in a light sheet microscope? So in a conventional light sheet microscope, you have the separation of illumination detection, and you want to combine these 2. And so the question is how to do that. So when I was in Ansh Desser's lab, we came up with this idea. We called it coherent structural illumination light sheet-based fluorescence microscopy. So the idea is basically you now have 2 illumination. You create 2 light sheets, and of course they will interfere on the sample plane here. And to rotate this pattern, we basically use these 2 scanning mirrors, and then they rotate at the same time. So correspondingly, this interference pattern also rotated. So in principle, it works. So this is some ER structures in the E cells. You can see this is a wide field image. This is a deconvolved wide field image. This is what we got from the structural illumination light sheet microscope. And of course, you can go through different planes. Like this is plane 20, 26, different planes here. You can compare the image from the wide field or the deconvolved wide field or the structural illumination. And here are some profiles. So in principle, this works, but the problem is it's super difficult to use. And the field of view is also very, very small. So as you can see here, this is the 1 micron scale bar. So we probably only get like 10, 20 microns of the field of view. So practically, it's not super useful, but the concept is there. So now we have the OPM system, and we want to combine the OPM with the structural illumination. And it is maybe possible. So basically, if you look at this part here, we create a light sheet here. If we can generate 2 light sheets, and then they have the interference pattern, now we have the structural illumination pattern. We can do sim here. So to generate that 2 light sheets is basically very simple. So if you look at the big focal plane of the objective, there's a line here, then you create a light sheet. If you have two lines here, then you create two light sheets here, and then they interfere, then you have the interference pattern. But then the question is, we want to rotate this pattern. You may remember that you need to rotate a pattern to get isotropic resolution improvement. So to rotate this pattern now is the challenging part. So of course, the very naive way is you somehow rotate the patterns here, but correspondingly, you also need to rotate your whole image system here. Of course, this is super slow, super bulky, and it's almost impossible. You can use this so-called Abe-Kunig prism, so that can rotate your image, and this might be a possibility, but to rotate these things is still too slow, and we want to image things fast, because one advantage of SIM is compared to other super resolution techniques is you can do that faster. So we want to do that still with the Galvo mirrors. So that's why we came up with this idea, the image rotator with the Galvo mirrors here. So basically, there are two Galvo mirrors here, and there are some folding mirrors, and there are 3 stacked mirrors here. So what you can see here, there are 3 stacked mirrors, and the light comes, or the image comes in one direction here, goes up, and while this Galvo mirrors is rotated, it would put the light or the image to these 3 different stacked mirrors. And as a result, if you can see the sparkle here is from one side, you can see it's rotated when we manipulate with these 2 Galvos. So now this is very cool. So basically, as I said, that you just manipulate with these 2 Galvos, and you put then you can detail the light. Sorry, not detail. Redirect the light into these 3 different stacked mirrors. Then you can rotate your illumination and also the image. So basically, we put this device or this image rotator at the image space here. So now we can basically create 2 light sheets here, and then through this image rotator, then we can rotate the image, the structure illumination pattern here. And when we collect the image here, after this this image rotator, it will still be stacked here, so we don't need to rotate this detection path. So as a result, in the past we create the whole stack. This is so-called parallelepiped volume. Now with this interference pattern, we can have this parallelepiped volume with the structure illumination pattern. And of course, we acquire the stacks in 3 different orientations, and through the regular SIM reconstruction, then we can get a higher resolution from of the image. So here is some results. This is 15 nanometer beads in agarose, and if you zoom in here, now you can see we increased the resolution from about 300 nanometers to up to 150 nanometers, which is about 2 times resolution improvement. And here, just showing you the comparison of the wide field image, the deconvolved wide field image, and the structure illuminations images on our OPM. And of course, we can do this live. So this volumetric acquisition rate is 1.2 Hertz. So this is 0.82 seconds per volume. So yeah, this is the dynamics of the mitochondria in U2OA cell. If you zoom in here, you can probably appreciate the fission of the mitochondria. Here is another example. So again, it's a mitochondria. This is color-coded in depths. So different color means different depths here, and then I hope that you can also appreciate the fission and the fusion of the mitochondria. Oh, I'm running a little bit slow. Oh, okay, cool. I think I still have some time to talk about this light projection imaging, which we actually published some years ago. So the idea of this light projection image is, imagine now you have a volume here, and then you can shear this volume or you can also rotate this volume. And if you look at the projection of this volume, you will realize actually this shearing and this rotation will give you the same result. It's not exactly the same, but you just need to apply some scaling factor, then they will look exactly the same. So this is very interesting because now if you acquire a volume, you imagine you have what kind of some worms or some embryo here, you acquire a stack and you do the shearing and you do a projection here, then it turns out that you are actually seeing like this sample is rotated. And how do we do that is basically now you acquire this volume like that. You have different planes through Z, and while you are acquiring this data, you also put two mirrors here, and then you can basically replace each plane into different X here. We actually realized you don't need to have two mirrors here, but in our first setup we used two mirrors. So basically this is a shearing effect. So this is our setup. It's pretty simple. You basically just need to put two mirrors in front of your cameras, and when these the motion of these mirrors are synchronized with the Z stage here, then you can basically do a live shearing. And why this is very useful? Sometimes I feel this is practically very useful, but some reviewers will say, okay, this is not a huge invention. Practically useful is not really science. But if you have an OPM system, or if you have a lattice system, you would. I was in the lattice workshop this afternoon, so you would immediately find that because of the lattice light sheet setup, you have really high resolution. You don't want to. You usually would do a sample scan here. So imagine this is your sample or cells here, and then to acquire data, you basically scan this sample in this direction. So what end up is your raw data will look something like this. Like you have a salami here, and you chop it, and you actually stack them together. This is your raw data, and it doesn't look like a salami, and it definitely doesn't look like a cell. You cannot really distinguish. You cannot really tell if it's a cell or if it's a good cell when you are looking for your sample. So usually you need to do some post-processing. But now with this live shearing, when you acquire this data, you can also shear all these planes to what it should be. Okay, so this is normally an image you would acquire, a raw data you acquire with such a setup or in the lattice light sheet setup. But now with the live shearing, you can actually shear this data on the fly. So now while you are acquiring this data, you also, shift these images here, and then if you can do that, and then if you make a projection, then now this looks like a cell, looks like the cell you want to see. And if you can do this in one exposure time, then you can definitely very easy to find your sample. And then, as I said, this shearing is very similar to the rotation. When you apply different shearing amount, it's like you are rotating your sample. So what you are seeing here is actually a cells on the cover slip, and we just acquire the data by applying different shearing effect, and there is no rotation of the sample or the system. It's just that two cover mirrors, and you can see it looks like the cells are rotating here. You can also do this on the conventional light sheet setup. So here is the vasculature of the zebrafish, and again we are just playing around with the shearing amount, and you can see it looks like the sample is rotated. And here is one example why I say this is very practical, because this is normally what you will see in a OPM system or in a lattice light sheet setup. But now with this live shearing, you can really just look around your sample and find the best sample you want to image. And because this is done in one projection, so basically you can do very fast imaging. So for example, this is a high, this this neuron firings, we acquire that with 20 Hertz. So this is every 50 milliseconds. This is another example. You can do fast imaging, and you can also play around with the shearing effect, amount. So you can image this while you are rotating, kind of like why I shouldn't say rotating, but it's like you are looking these cells from different angles. If you could actually image from 2 angles very fast. And if you have a red-green glass here, you can see this is kind of a anagophy. So you will look like a stereo image if you have a red-green glass. And of course, you can also play a little bit with this. So you can put a beam splitter and you play these gavel pairs in front of one camera. So now you can look at the sample from 2 angles simultaneously. So here is an example of a zebrafish heart, and you can look at that from 2 angles. And we image this with 10 Hertz. Another nice thing is we can also combine this projection with the OP sim. So now instead of acquiring the whole stack, we can just acquire the projection here, and you can again do the sim reconstruction. So this work has been we put out on the bioRxiv, but it has been recently accepted, and it should get published soon. And as a result, this is the projection sim, OP sim. So this is the projection of the wide field image. This is the projection of the OP sim images. And now we can image this even faster. So this is 2.7 Hertz with the exposure time of 40 milliseconds. And we can also do this with the, this is another example. This is the mitochondria. We imaged that with 2.2 Hertz. And then I hope that you can still appreciate the resolution improvement and the fission of the mitochondria. Oh, okay. So I want to sum up here. So I still give you some brief introduction of the light sheet fluorescence microscope. Just remember the advantage of light sheet is it has low photo-bleaching, low photo-toxicity, and it has intrinsic optical sectioning, and you can do that fast. Something is very, very important is we also have the ASLM system in the lab, which is the so-called actually sweep light sheet microscope. And I think this is very useful for the clear tissue imaging or expansion microscopy, which I didn't have time to mention that today, but this is now becoming a very big field in the light sheet community. So I talk about combining SIM and light sheet fluorescence microscope. It's very challenging, and we have some solution, but it's still very challenging. So now we have the new method to combine OPM with SIM, which has been published here. And the most important work here is we invented an image rotator that can do what we want to do. Light projection imaging, we have published that some years ago, and I hope that you can appreciate it's practically very useful. And now we also combine that with the OP sim here. Our recent work is now when we build this OPM system was aiming for higher resolution, but actually we can also do that with a mesoscope. So we also now created a meso OPM. It has been recently accepted by Optica. It should get published soon, but if you want to, if you can wait the publication, you can also look at this bioRxiv paper. And then in the end, I would like to thank all the people who have worked with me or helped me, and especially Recto and Bingyin. And then I think I still have some time to answer questions.
Thanks for the great talk. Maybe a bit technical, but you have your secondary objective and your tertiary objectives as naughty. But how do you decide in what angle you position them?
So basically, you can play around with the angle. So what we usually end up is we want to collect as much angle as possible. So because you don't want to lose the resolution, and you also don't want to have the light sheet coming with a very steep angle. So I think now with our system, most of the time we use 45 degrees of the light sheet angle.
So, but you actually would want to go to 50 degrees or 55 even. Is this something you practically determine, or do you actually calculate certain degrees that you need?
I don't remember exactly now, but you need to compromise, different parameters. So I think in the end, most of the time we use 45 degrees.
Okay, and then maybe one more question. How stable is your system, like a regular OPM system that you're using? And what do you think is the most critical parts to keep stable, the system stable? What misaligns the easiest?
Are you saying about the stability of OPM or OPSIM?
OPM, the OPM.
Okay, so for OPM, it's quite stable, I can tell you. So one of our colleagues in the lab, he is a biologist, and we have many different light sheets set up in our lab. And he seldom uses it because it's just too difficult to use. Well, it's not that difficult. I feel it's quite useful for me, but for him, it's a little bit difficult. And then one day we built this OPM system, he started to use it. And you can see how user-friendly is that OPM system. And it's also quite stable for the OPM. But for the OPM SIM, it's not that stable because a little drift of one optics would destroy your whole patterns or your whole reconstruction. So for that, it's more tricky.
Are there other questions? Okay, if not, I have some question. I was wondering, in your shearing approach, are there some limitations in terms of the size of the sample or the size of the field of view?
No, so no, there is no limitation. So the field of view is limited by basically your camera. So whatever you can image with your camera, you can see that the shearing. Of course, you can shear to, I think you cannot shear to 90 degrees, plus minus 90 degrees. But within plus minus degree, it's all possible.